Okay, can you see that screen? Wonderful. Okay, anyway, I gave this title to Cecil some time ago, and then I thought about it again last week, and I had to start thinking about how to present a talk. And I just wanted to acknowledge my previous work with Ken Hover and the late John Bickley on working on performance specifications. And as I said, the devil's in the details, and for this presentation, I've selected the Tasmanian devil to represent the devil. But first, I'll talk about Calvin. I had the pleasure of working with Calvin and his enforcer, Ken, on a big project recently. I learned a lot from Calvin on a big resolution dispute claim on a large project. I took some notes on this profession. You can see all the signs of a professional. You got a cell phone, got rolled up notes. He's got a serious look on his face. At least I think it's serious. So it was a lot of fun working with Calvin, and I echo some of the comments of others. Although I've never served on 301, I really enjoyed my interactions with Calvin in the last couple of years. And so the outline of my talk covers a number of points. Do we have sufficiently defined exposure categories and sufficient requirements for demonstrating compliance with those exposure categories? Do we have adequate performance test methods for assessing compliance? What kind of test methods can we use? And inspection issues. And I took the example out because of timing. And the whole issue of performance has been of interest for a long time. We did some work, Ken Hover and John Bickley and I back, and we produced two reports for the NRMCA P2P program in 2006, 2008. There was an ITG formed, I think Carino chaired, that wrote a report in 2010, and then ACI 329 was formed on performance requirements, and they published a report, and they're still very active moving forward in those performance issues. But the scope of 329 is limited to performance of the as-delivered concrete, and it doesn't extend to the as-built performance of concrete structures. So it sort of stops at the chute of the truck. And so in terms of durability, I think there's more to obtaining durable concrete structures than the stuff that's delivered out of the truck. So this year, one of the changes, TAC has approved formation of Committee 321 Durability Design Code, and I helped get that code formed. Larry Sutter is the chair of that. The idea is to establish both design and construction requirements for obtaining durable structures and other concrete applications. And we're trying to make it broader than structures, because 318 is limited to structures, so we're looking at all concrete applications. So we're looking at exposure classes that would encompass other things than buildings. And also looking at trying to include better performance alternatives and direct durability requirements to meet these exposure classes, and not just the prescriptive or indirect strength and water cement ratio limits that currently exist for the most part. Now, there's all kinds of deterioration out there that affects durability. And all of them are affected by fluid ingress rates. I'm going to focus just for the talk on chloride corrosion to save time. So even though the fundamental issue with preventing chloride corrosion is to restrict chloride ingress to the reinforcing steel, the current 318 code only provides a strength requirement and a maximum water cement ratio limit. And there's only one exposure class for all chloride exposure, C2. There's no direct requirements to address the obvious issues that one would think of, like limiting rates of chloride penetration. Do we need any additional cover? Do we need additional curing? Issues limiting cracking, talking about thermal control plans and shrinkage, which was just mentioned by Henry. And inspection to make sure that you're getting the things you think you're getting on site. Are you getting the cover depths that were specified? Are the curing practices being carried out adequately? And one of the issues, as I mentioned, the only exposure class for chlorides in ASC 318 is C2. Doesn't matter how severe it is or what the cause of the corrosion is, whether it's marine corrosion, de-icing salts, or saline soils, it's all C2. The C1 exposure, which is the only other corrosion class in 318, is just wet environments without chlorides. And the only thing I can think of is that this is assumed to be related to carbonation corrosion, but they don't mention carbonation anywhere. And there's no performance requirements, as I mentioned, for limiting the rates of chloride ingress. There's no, the cover requirements in 318 are only based on the need for fire resistance and for obtaining adequate bond. There's some very loose language saying, well, it's up to the designer if you want to add some more for severe exposures. And curing requirements in 318 are only set there to obtain adequate strength, mainly for the test cylinders. And it doesn't assess the quality of the cover, curing for the quality of the cover, protecting that outer part of the steel, or protecting the steel. As opposed to 318, for example, just the United Forces guide spec has 5 exposure classes just for marine exposures. Directly exposed to salt water, subject to severe abrasion and exposed, directly exposed to marine atmospheres, protected from direct exposure from atmospheres as marine atmospheres, and then buried in soil. So they've got requirements. They have a limit on permeability using the 1202 test of 1,000 coulombs, or they have an alternative bulk or resistivity limit. They also have minimum requirements for the minimum amount of SCMs to use to get that permeability. Not maximum levels like 318, but minimum levels that are required, which is quite a different take on things for a marine environment where there is severe problems. Other codes in the world, EN 206, the European code, just for chlorides alone, has 3 exposure classes. There's the 318 with 1. The Chinese code just for marine exposure has, just chloride exposure, they have separate for marine exposures, has 3. The Canadian code has 5. The Australian code has 3, just for soils. And they have a separate requirements for marine exposure. And most codes also have special exposure classes for carbonation exposure. Carbonation corrosion of steel is another thing that generally gets ignored in North America. And just on this airborne marine exposure, because it's a deficiency, I think, in 318. The Australian code talks about chloride exposures for sea spray that can go in beyond 50 kilometers, so it's moderate there. But even at their high exposure, it could be up to a kilometer, almost more than half a mile in from the shore. It can be a very high exposure just from airborne spray of salt water. And so it's something that's not addressed in 318 at all, and this has led to problems. Structures built near the coast, like these condos in South Carolina, they're well back from the shore. They're not directly exposed to salt water, but they're exposed to salt spray, and you may be able to see this. The soffits are all corroded after a short period of time. And that's a big problem with a lot of buildings along the shore in Florida and elsewhere. Over in California, I looked at this garage earlier this year. It's a quarter mile in from the ocean, and it's severely corroded. In fact, it's a 3-floor garage, but they've condemned the upper 2 floors. They only have cars parked in the lower floor. And it's not directly exposed to chlorides, but it's ocean spray with salt. But that wouldn't be considered a C2 exposure in 318, at least not clearly. One of the things we've been looking at to try and look at this, and this is part of the first straw man from the 321 Durability Code Committee, is let's fix these exposure classes, be a little more clear on what we mean. So C0 is no exposure, that matches. All the C1 exposures, no chloride, so we'll call those carbonation exposures. Better define them. And then we'll divide the chloride exposures, all the C2s, into de-icer exposures with various severities. And then marine exposures and saline soils will have those maybe three there. We'll deal with the airborne spray, submerged and tidal and splash zone, which tend to be the most severe. And let's up the requirements. We could have strengths and water cement ratios like now. And we could define curing requirements with increased amounts of curing required for different severity. The CSA code does that, for example. We could have increased cover requirements for these severe environments. These are just straw man numbers. I just threw them in the table. And instead of specing maximum water cement ratio, and perhaps water cement ratio and strength, you could have a performance option. This is either to use the ASTM C1202 or the resistivity method, which is the ASTM 1867. And so there's two values there. That's the Coulomb value, that's the resistivity value in ohm meters. And you have increasing requirements as the severity got worse. So this is just a real straw man thought process, but the main thing is to better define the exposure classes for the severity of the exposure. And not all these things are relevant to buildings, but they are relevant to all type of concrete that's being placed. Okay, so as examples, the sulfate exposures and the freeze-thaw exposure classes are generally are pretty adequate. But the chloride one, I think, is this corrosion exposures, the C exposures, I think are not dealt with adequately in 318. So we have exposures. What about performance tests? People generally say, well, we don't have adequate performance tests. There's problems with all of them. And tests are being developed. The resistivity test was standardized late last year. But waiting for the perfect test is a barrier to moving forward with performance. Progress results from action and common sense, or what Henry called engineering judgment, as well as academic compliance. These are John Bickley's words from 2011. And nearly all the essential properties of concrete can be measured to a practically acceptable level, provided that implementation is covered by appropriate procedures. And these procedures need to be incorporated in codes and specs. So durability of concrete depends on preventing nasty things from getting in via fluids through the pores. We need precise and accurate methods or reproducible methods relevant to that. And these tests need to be simple and as rapid as possible if you can use them in specifications. And we need appropriate acceptance limits for these different exposures. So some of the details that are needed in adopting. Now, a lot of service life models assume that chlorides move in by diffusion. They slowly diffuse due to the concentration gradient, and they move in towards the steel. And there is a standard test, ASTM 1556, which was built on the Nord test method that existed before that. You cast concrete, you cure it for 28 days or whatever, and you seal it on all sides except one. You let the salt penetrate in of a certain concentration for at least 35 days. You profile grind it. You plot the data, fit it to a curve using a best fit equation, and you can calculate this diffusion coefficient from that using Fick's second law. And that's used as an input in many service life models. However, this is a very labor-intensive test method. It may be suitable if you have lots of time in advance of a project for pre-qualification purposes on major projects, but it's really not suited for acceptance. So for acceptance, we need rapid test methods. And test methods to be rapid are typically index methods. They don't provide a direct value that maybe could be used in service life models, but they're index methods. They give you an indication of that fluid penetration resistance. So they're more practical and potentially usable for QA/QC purposes. And there's several. I'm going to talk about 4 of those methods: 1202, this Nord test method, rapid migration test, the surface resistivity that's been adopted by AASHTO, and the bulk resistivity adopted by ASTM. But even so, which one you pick? You're not going to specify all 4. You've got to pick one. You can't have competing limits with different test methods, or you'd have a real dog's breakfast. 1202 has been around since the early 80s, developed by Dave Whiting at the PCA many years ago. And it's really an awkward conductivity test. It's a rapid index test that measures the conductivity of the concrete. You saturate the concrete, you put it between 2 conductive solutions, you apply a voltage, you measure the current flow, and you multiply that current over the 6-hour time frame to get coulombs, which is the charge passed over the 6 hours. And there's people who complained about that test method. But in general, it has worked. I think if Dave Whiting was alive today, he wouldn't pick that test method now because things have evolved over the last almost 40 years. But it was a real advance at the time. And a number of specs used 1202. The Canadian concrete specification adopted C1202 limits in 2004. And currently, for example, in one exposure, which is our standard sort of the equivalent of a C2 exposure at ACI, so 35 MPa, which is about 5,000 PSI, 0.40 max water air entrained, we require 1,500 coulombs. We've set the limit at 91 days because if you set it at 28 days, the only way you're going to get there is with silica fume. If you set it at 91 days, then things like slag and some fly ash mixes can also make that limit. And for the purpose of 1,500, we say that this is, if you're going to use it for acceptance, but we say it's the average of 1,500 coulombs for the three most recent test values can be used for pre-qualification purposes to qualify a mix. So you don't have to make new data, you can take the three most recent values. Say if we've been doing this mix, we get to 1,500. For acceptance, then we say the running average must be less than 1,500, with all individual test results less than 1,750 to allow for the variability of the test method. We know there's variability in the test method, and we don't want to start rejecting concrete because one value is high. As I said, it's not useful to pick 28-day limits for concretes containing things like fly ash and slag that develop their performance at later ages, because then you just eliminate them, unless you use this accelerated 28-day curing that is an option in 1202. And just to show the sort of change that can occur, you get big reductions in time, 7, 28, 56, 91 days. We set our limit, the one I just mentioned, at 91 days. So Portland cement concretes on their own probably won't make it or be just on the edge. Whereas the slag mixes, these are all slag mixes here, these next four, they all make it handily. In fact, they would make it at 56 days. If you use silica fume and slag, you can meet it at 7 days. The silica fume reacts so quickly. But we don't want to make that our only option. So the C1876, which was just recently standardized, a fairly simple concept. You take a saturated concrete again, you calculate the resistivity, which is the resistance to electric flow, calibrated for the, or normalized for the area of the sample and the length of the sample. So resistivity is a material's property, and there's all kinds of commercial equipment. These are just three of them that I happen to have in my lab for measuring that meets C1876. Now we have this limit. Nobody's adopted it yet. We put it on the books so people can get used to it. We've done the same thing in the Canadian spec. And the Canadian spec we expect for the 2024 edition to have introduced limits for resistivity as a faster alternative to C1202. So instead of taking 6 hours to run the test, you can get a result in about a minute with these test methods. It's much cheaper. In fact, you can do it on the same cylinders you're going to test for strength, which means you don't have to cast extra specimens. You don't have to cut slices and all that. You can take the cylinder out of the moisture room if the ends are flat or ground flat or sliced, and you measure the resistivity, then you can cap it or whatever, however you're prepping the ends and test strength. Now, the DOTs got excited some time ago about using surface resistivity. I think the real reason they got excited is they thought they could use it in the field, which again is fraught with difficulties. There's 4 probes, it's a surface measurement, and you apply a voltage over the middle 2, which sets up you apply an alternating current over the outer 2 electrodes, which sets up a flow net equipotential lines. You measure the voltage drop over the middle 2, and you can calculate the resistivity, again, from the voltage and the current and the area of the core of the cylinder. And you do this a whole bunch of times in the AASHTO 358, get an average value. Now, trouble with surface, in my opinion, the surface resistivity is subject to more issues because the surface is, unless it's adequately saturated and hasn't carbonated, and a whole bunch of issues that need to be addressed before you can get to meet useful measurements. So the other one, bulk resistivity, you're measuring the bulk resistivity right through the whole area of the cross-sectional area. This is you're only measuring a surface value. The other one that has been used, and I know one of the consultants used in that recent bridge that was built in New York, across the New York Harbor, was adopted this test method, this rapid migration test. In a lot of respects, it looks like the C1202. Got a sodium chloride solution on one side, sodium hydroxide on the other. You apply a voltage. But in this case, instead of putting 60 volts in, you measure the initial current flow through the concrete and you pick the voltage based on that and the time of test on that, because what you do at the end of the test is you split the cylinder disc open and you spray it with silver nitrate, and it turns white. If it's where the chloride is penetrated, as it turns to silver chloride. And where the silver nitrate persists, where there's no chlorides, under light after a few minutes, it turns dark brown. So you can visually see the chloride penetration. You can measure every centimeter across or half inch across, get the average penetration. And you can actually plug that depth into the equation. This equation here, which looks complicated, but it's only temperature and length and voltage and time. And there's the penetration depth, and you can calculate a non-steady state diffusion coefficient, which some people use in diffusion in service life models. So people have jumped on this in Europe because you got a diffusion value. I'm not convinced that diffusion value is the right one to use, but anyway, that's fine. It takes a little longer because the period of time of the test could be 1 to 4 days, depending on the quality of the concrete, because you're using much lower voltages. So anyway, there are different tests, but now one of the things we need to worry about, and I published a paper last year in Cement and Concrete Research talking about, well, how reproducible are these methods based on published results? And people complain about the C1202 test being too variable within lab or between lab, but a lot of these other test methods are in a similar range or worse, like the NT492 I just mentioned. The bulk resistivity method, 1556, is also more variable than that. And these resistivity tests are somewhat better, but we're actually ASTM's conducting interlab testing now. We're redoing the 1202 values, this new resistivity test, and we're going to redo the bulk diffusion test. Unfortunately, we cast all the concretes and distributed to all the labs around North America just before all the shutdowns due to COVID-19. So we've had to delay the testing. We're just getting the testing underway now in our lab in the last month. So the results are going to be delayed and getting better information on how reproducible these test methods are. So, okay, we have test methods, we have exposure classes. When do we test? And I took this from Ken Hover. We want to pre-qualify mixes. We want to have information on how good the mix is before, when you're bidding on a job. When it arrives on site, you want to do some testing to identify that it's the same concrete you pre-qualified. And then often we do acceptance at the chute. We do cylinders and whatever else at the chute for acceptance purposes. Some people like to do it at point of placement because pumping or other transport of the concrete may affect the results. But the owner doesn't care about any of that because the owner wants a structure that meets the requirements. So they would prefer in-place testing, and some highway departments have gone that route. And so if we adopt performance testing, we need a pre-qualified mix that can meet the spec, or when it gets on site, that it's the same concrete that was delivered, as I mentioned, and it meets the spec. In-place testing, we've got to take cores or do NDT tests that on a statistical basis show that not only the concrete, but the placing and curing methods also meet the performance levels that have been predefined. And one question comes up is, should we use the same acceptance limits in all cases? An example of that, and I took some data from a paper that Karthik Obla and Colin Lobo wrote some years ago. This is what they would do. If you spec 1500 coulombs in 1202, then the producer, to be confident they're going to meet that on arrival, need to target something lower. And if you're going to test in place, you've got to say, well, look, we need some value for acceptance, which could be 1500. But then they have said because of the variable, they would go up to 1850 for a single value. It differs from what we adopted in CSA, but it's in the same range. So you allow for single values that exceed that as long as the average stays below the spec value. Now, for pre-qualification tests, some of the things that John Bickley and I worked on several big projects, and it's been used in a number of projects since then, is using what they call monolith tests or for mass concrete or other large elements. And a lot of things, because of the high cement contents that are used now, even small elements, less than half a meter in cross section, can be considered mass concrete because of the amount of heat that's generated. But we cast these elements in 1 meter cubes, insulated with 2 inches of foam insulation inside plywood. We preset thermocouples and we cast the concrete, and concrete suppliers have got to pre-qualify their mixes, and they do that. The 1 cube here is the one they're just finishing off now. And we monitor the temperature profiles that develop and do the testing on the pre-qualification testing on these blocks. So for example, here's a slag with 50% slag, mixed with 50% slag. They were looking for a 55-degree maximum, but it was exceeded. This one didn't quite make it. They were looking for a 20-degree C maximum gradient through the cross section between the inner and the outer part. They made that. In this case, the placing temperature was 25 or about 78 degrees Fahrenheit. And this shows over a 10-day period what's going on. Here's the ambient bouncing around. Here's the near surface bouncing around. And here's the core going up and then back down again over a 10-day period.
We have 5 minutes, Doug.
Okay. And here's another one that we used larger aggregate and was cast in cooler weather, and we did meet the 55 degrees C in this case. And this shows over 14 days. We used this on one project with a big slab, a 2.2 meter thick slab, about 8 feet thick, large single placement, heavily reinforced, and we used large aggregate. We had a spec of 55 degree max and 20 degree differential. And they used wireless sensors. They instrumented this slab, and they met this thing. This is over the first 3 days. It maxed out at 54 degrees. The maximum gradient at one place was 21, but almost everything was met the 20 degrees. Okay. One of the problems we have is I'll skip by this, but one of the biggest problems we have is measuring water. We have water cement ratio specs, but we can't measure it. The only test method, and AASHTO has a standard for this, I know CSA has one too, is the microwave test for water content. Because cement materials and all the solid materials are generally well controlled at the batch plant. And mixed water is well controlled at the batch plant. But then after that, we don't know what else water is in there. There's water that was left in the drum from the previous load. The aggregate water is not always well defined or well measured. There's trim water added to get the slump up. And then what I call keeping the contractor happy water when it arrives on site, because the driver wants to get along with the contractor. So the microwave test at least offers a way of looking at the uniformity of the water. So uniformity is important. You don't want different loads arriving with different water contents. And I forgot about finishing water. Fine example of adding water on site as the concrete gets away from them. But typically we measure slump and air on site. We might measure rapid chloride permeability, and we measure strength make cylinders. But the owner wants in-place tests, as I mentioned. A number of agents like our Highway Department in Ontario has been using end result specs for the last 20 years, and they assess performance and make payments, penalties, and bonuses based on whether statistically based cores results meet the requirements for strength, for air, for rapid chloride permeability. And they also want to look at what's the in-place control, and this is where 301 has thermal control plans, controls on shrinkage. What do you do if there's shrinkage and crack? What are you doing to prevent cracking? You want to minimize variability, and you want to do that in advance, especially with things like cover. You can measure cover after the placement, but that's too late to do anything about it. What you'd like to do is measure it before. A lot of specs allow plus or minus half an inch on cover. This is some data from the UK showing a bunch of bridge columns. They had 30 millimeters cover, like an inch and a quarter, but the standard deviations is just over about half an inch, which means a whole bunch of the cover is down about a quarter of an inch, which isn't very good. We did a parking garage in Toronto at the airport, and the engineer made the contractor check the cover required before each placement in the parking garage, very large garage. They were looking for a minimum of 40 millimeters, which is just over an inch and a half, but they ended up with an average of 50 or 2 inches, and the standard deviation was only 1/8 of an inch because they measured it before they placed the concrete. And so the uniformity in terms of corrosion resistance is going to be greatly enhanced because there aren't any of these bad ones. So we need to measure performance. Measures of performance will offer improvements over existing strength and water cement ratio limits. We need standard test methods that are reliable and appropriate test limits. We think these tests exist and have been used. Waiting for perfect test methods is not good engineering. We always need better test methods, and these will develop over time, and they can be adopted, and existing test methods can be replaced. We need to set statistical limits and appropriate test ages in the specs, and we need to use good engineering judgment. And finally, speaking of judgment, this is Cal. I had dinner with Cal at the end of this big project, and he was considering the deep questions over dinner, such as this. So here's to Cal. What a great guy, and thanks for the opportunity to speak in his session.